Alright, so in this video, I'm going to solve the equation 3 to the power of x is equal to 15. So my only variable in this equation is x, so that's what I'm going to be solving for. And now for my solution. So let me first start by rewriting my equation down here. So 3 to the power of x is equal to 15. And 15, I can rewrite this as 3 times 5. And now I'm going to take the log on both sides. So I get log of 3 to the power of x is equal to log of 3 times 5. And if I have something in the form log a times b, this is equal to log a plus log b. So log of 3 to the power of x, this is equal to log of 3 plus log 5. And if I have something in the form log a to the power of b, I can move the b to the front, so I get b times log a. So log 3 to the power of x, I can move this to the front, and I get x times log 3 is equal to log 3 plus log 5. So now from here, I'm going to divide both sides by log 3. So for my left-hand side, these two cancel out, and for my right-hand side, I get x is equal to log 3 plus log 5 over log 3. And this is the same thing as log 3 over log 3 plus log 5 over log 3. So log 3 and log 3, these two cancel out, so I get x is equal to 1 plus log 5 over log 3. Now, log 5 is equal to 0.6990, and log 3 is equal to 0.4771. So this is going to equal 1 plus 0.6990 over 0.4771. Now, 0.6990 over 0.4771 is equal to 1.4851. And 1 plus 1.4851 is equal to 2.4851. So this is my value of x. Now make sure to subscribe and leave a like, and thank you. Bye. Alright, so in this equation, I have 1 to the power of x is equal to 3. So this might seem like an impossible equation, right? Because how can 1 be to the power of any number and equal to 3 if 1 to the power of even a million is still equal to 1? Well, let's try to solve this equation the way we would solve any other exponential equation. The first thing I would do is take the natural log, or ln, on both sides. So I get ln 1 to the power of x is equal to ln 3. Now, if I have something in the form ln a to the power of b, I can move this exponent b to the front, so this is going to equal b times ln a. In this case, I have ln 1 to the power of x, and I can move x to the front. So now I get x times ln 1 is equal to ln 3. And now if I divide both sides by ln 1, these two cancel out, and I get x is equal to ln 3 over ln 1. Now, if you guys already didn't know, ln 1 is equal to 0. So I get x is equal to ln 3 over 0, and you can't take any number and divide it by 0 because that's undefined, meaning this has no solution. So that method doesn't work. However, this just means that there are no real solutions. But there are different types of solutions. So what I'm going to do to solve this equation is, first, let's recall Euler's formula. And if you guys don't know what this is, it states that if I have something in the form e to the power of I times theta, this is equal to cos of theta plus I times sine of theta. And I know this may seem a little complicated right now, but just bear with me. So let's say that theta here is equal to 0. So if theta equals 0, then I get e to the power of I times 0 is equal to cos of 0 plus I times sine of 0. So then I get e to the power of 0 is equal to 1, cos of 0 is 1, plus sine of 0 is 0, and 0 times I is 0. So 1 plus 0. And e to the power of 0 is 1, so I get 1 is equal to 1 plus 0. Now, what if we say that theta is equal to 2k pi? K being a constant, so it could equal any number, 1, 2, or 3. So if I plug this in, I get e to the power of I times 2k pi is equal to cos of 2k pi plus I times sine of 2k pi. Now, what if k is equal to 1? What if our constant k is equal to 1? Then I get e to the power of I times 2 pi is equal to cosine of 2 pi plus I times sine of 2 pi. Now, cosine of 2 pi is 1, and sine of 2 pi is 0. So I get this is equal to 1. Now, if k is equal to 2, I would get cos of 4 pi plus I of sine 4 pi. Cos of 4 pi is 1, and I times sine of 4 pi is again 0. And if I do the same thing with 3, I would again get 1 plus 0. So this pattern continues, and it keeps on equaling 1 no matter what value of k we get. So we can say that e to the power of I times 2k pi, this is equal to 1 no matter what value of k we have. So now this means that we can substitute this in back to our original equation, which is 1 to the power of x is equal to 3. This is our original equation, and we can substitute in 1 for e to the power of I times 2k pi. So now I get e to the power of I times 2k pi to the power of x is equal to 3, and this is my new equation. So now, to solve this, I'm going to do what I did at the start. I'm going to take the natural log or ln on both sides. So I get ln e to the power of I times 2k pi to the power of x is equal to ln of 3. Now, if I have something in the form ln a to the power of b, I can move this exponent b to the front, so I get b times ln a. In this case, I can move x to the front, so I get x times ln e to the power of I times 2k pi is equal to ln 3. Now, I'm going to use this property again and move this to the front as well. So I get I times 2k pi times ln e is equal to ln 3. And ln e, these two cancel out. So now I'm left with I times 2k pi is equal to ln 3. Sorry, and I also have x. Now I'm going to divide both sides by I times 2k pi. So when these cancel out, and I get x is equal to ln 3 over I times 2k pi. Now I'm going to multiply this by I over I, which is the same thing as 1. So I get x is equal to I times ln 3 over I times I squared, and if you guys already know, I squared is equal to negative 1, so over negative 2k pi. And k, in this case, can't equal 0, because if k were 0, wouldn't work. So this is my solution to this equation.